Okay, good afternoon, everyone. Let's start our 99th session of the seminar of EDP and Applied Mathematics. Today we have two excellent young speakers. From one side, we have Yue Wang, which will be presented by Diego. And on the other hand, we have Laurent Prouvé, from Brazil, which will be presented by Juan Limaco. Okay, Diego, you can start.
Okay, so for me, it's a great pleasure to present Yue Wang, junior research group leader at Langer University. She graduated in 2009 in mathematics and applied mathematics from the Fudan University in Shanghai. She's an expert in the area of control theory for PDE and applications, especially for hyperbolic system and related topics in modeling, analysis, and control design, synchronization. And today she's gonna talk about Rondo-Bach method for optimal control of networked 1D hyperbolic systems. So thank you very much for accepting deliver a talk in our seminar, and the word is yours.
Okay, thank you, Diego, and thanks for the invitation from John. This is a very great honor and pleasure to be here to present a very recent work with Dr. Daniel Wettman and also Professor Alex Zuazua. And in this talk, I would like to show you three things. The first is what is a random batch method. The second is how to apply it for speeding up the simulation and optimal control for hyperbolic PDEs. And thirdly, we end with some numerical examples and the convergence result. And this work is funded by my German Research Foundation and also Alexander Humboldt Foundation. So, move. Okay, so let us start with the motivation. Today, I restrict myself to my familiar field, that is one-dimensional hyperbolic systems on networks, the solution of which are wave-like, with finite propagation speed that we know. And you may see that in many real-world applications, for example, the upper two elasticity systems, like coupled vibrating strings, or highly flexible beams used on the wings of flight devices. The below two applications show the flow transported networks. It could be the pipe flow, such as the Euler equation to describe the gas flow on one pipe, or the open canal flow, such as the Seminario system. And currently in our chair in Erlangen, Germany, we are launching several projects in Europe and Germany on different type of hyperbolic PDEs, aiming to explore dynamics and control and numerical method for different mathematical perspective. These projects have applications, for example, the fluid flexible structure interaction or gas networks, or the damage problem in the mechanical system, and also some mobility project internationally. And for such network PDEs, one interest is to develop the real-time cable algorithm, let's say to obtain the accurate and fast prediction of numerical solutions and optimal control. And this goal has significant difficulties on large-scale network. Why? Because you may have to consider a large number of edges and complex transmission and topological structures, such as circles or loops inside. And we see it's possible to compute a faster solution when we record the stochastic method, which are quite successfully used in the optimization and training neural networks recently. And one approach inspired by this is called the random batch method. And the origins of random batch method is for speeding up the simulation and control of large interacting particle systems. So here, when we consider full interaction for these systems for n particles, the computational cost grows rapidly when n is large. So in 2020, the group of Xi Jing from Shanghai Jiao Tong University, who is a friend of Enrique, proposed a method for this problem. And I will explain to you the main idea in these slides. So, okay, now we have n particles. So first, we divided them randomly into a batch of size p. So in this picture, the p is 3. And I divide them by different color. And for each time step, we consider only the interaction in the same batch, sharing the same color here, and do a simulation in a short time of length h. And then we repeat that, another round of a random choice. And in formulas, you will see that the original problem has the size of n of ODEs, and it can be reduced to p equations on each step. So this algorithm shows the advantage that for such kind of ODE system, when the random batch solution converges to the original one when the step length h goes to 0. And meanwhile, it reduces the computational cost from n power to pm, and this p could be very small, which is just greater than 2. So in that sense, it's a very efficient and accurate algorithm to compute such a system. Then, following this work, Enrique has extended this algorithm to optimal control problems of particle systems. And one example is the guiding problem, where the driver, for example, the dog, aim to guide the invaders, the state of the ship, to a desired region. And this algorithm has been realized by MATLAB in our chair, and we share at the long night of science to all teenagers in the city of Erlangen, Nuremberg, and Fiat. So it was quite successful that the young students or teenagers could understand the basic idea of this algorithm and also have the fun to play this game. So this is one example to use this algorithm. We call it the shiphead problem. And the first mathematical convergence proof is given by Weidmann and Zuozhuai in 2022 in the setting of the operator splitting. And in that paper, they try to consider the linear quadratic optimal control subject to this kind of linear ODEs. And in short, this operator or the matrix A is split into M submatrix. And now in this random batch algorithm, we could assign uniform or various possibilities upon each subset of the identity set 1 to M. And we cut the time interval into small intervals of the length bounded by H. So for each time step, I randomly choose a subset of the S omega K and sum up the submatrix with a weight of 1 over the possibilities it would be chosen. And we define these randomized optimal control problems equipped by this new designed matrix, which is smaller or more sparse than the original matrix A. And this paper presents the convergence result for the solution itself and the minimizer of the optimal control problem in expectation way. But here, if you check this paper, that the norm of the matrix A is bounded. This is a very important assumption for all its estimations. So whether this algorithm can work for PDEs, and especially for the network case, because for PDEs, the operator A is unbounded. Then the mathematical problem is that its convergence theory and applications are hardly done in this region. And if you search online, very recently, there is a work done by Asman. They try to apply this algorithm for a kind of PDE, but it has a very general title, but indeed it's a very specific case for the parabolic type. So, and they consider a backward Euler discretization of such kind of parabolic PDE is not the continuous version. So that is not our case. So my work is to try to think how to apply this random batch method algorithm for the hyperbolic equations. And to answer this question, I first look into the following toy example you might know well. So to roughly give you impression, this is a Cauchy problem for linear transport equation with a bounded Lipschitz continuous velocity field V of x, and without controls now. And we consider its evolution. We can consider it as the evolution equation with a unbounded operator A. And now we again apply this random batch scheme on this system by splitting this operator A into n pieces. And in each time step, we randomly choose batch B of size P. So let's choose P sub-operator and sum it up. And this P over M over P is according to the possibility adjusted on this submatrix. And we are able to prove that the solution to these random batched equations converges to the original one in the expectation. So means in the space of possibility measures. And so now I will show you a simple example to understand how to split that. To be easier, so we consider a constant velocity v of which equals to 1, and only split into two continuous velocity function v1 and v2. And on each time step of time length, we randomly choose one of this velocity and compute the solution. So now the orange one is a randomized solution. You will see that it keeps the wave shape quite well. And of course, now the switching time is set as 0.01. And of course, we can see that in the convergence proof, when the switching gets faster, then you will get a more accurate solution, which stays closer to the original solution in black. And in the last slides for the transport equation, I want to show you that if I split the velocity field into two functions that are not Lipschitz continuous, for example, I just split the v at the node 0, and then it has a jump at the splitting point, then again, you will see indeed the solution is not very far from the original one, the black one. But of course, you will pay the price by lacking of the continuity. So it's not so smooth anymore. But this simulation and the first attempt in the transport equation give us some evidence or the confidence to think that, okay, so it seems that the random batch method also works for PDEs, especially for hyperbolic case. So we can think to apply that for more complex case. So now in the general way, I consider a very general hyperbolic systems after scaling. So then it can be used to describe all networked first order hyperbolic systems. And here the state function y has n components ordered in the way that the first p equations are with positive real eigenvalues, and the left n minus p states traveling along the negative characteristic curves. And now the boundary conditions or the transmission conditions is summarized as a state into the domain can be written by the state leaving the domain. And this is a type of boundary conditions to promise the well-postedness of the system. And now, of course, it with a boundary coupling matrix K. And you will see that I allow the coupling in the equation and also in the boundary. And for the control setting, we allow the distribute control happening in the equation and also the boundary controls. So for well-postedness, the compatibility conditions at the boundary nodes or regularity assumptions, of course, are required. And again, we apply the randomized splitting scheme on these equations, where now we not only splitting the matrix lambda, which describes the traveling of the waves along each edge, but also the internal coupling matrix G and the B in front of the distribute control. And okay, so the randomized splitting scheme in formulas are as follows. So first, splitting the matrix lambda G and B into submatrix lambda M, GM, and BM. And step 2 is to divide the tan interval into small pieces of maximal length H. And on each tan step, I just choose a part of the matrix and sum it up. And by this way, you will see that the expectation of the new matrix goes back to the original one. And now we arrive at the randomized system. So here comes the first question. Is the solution YH to this randomized system a good approximation to the original one when H is sufficiently small? And correspondingly, we can address the optimal control problems with such a kind of PDE constraints. And we denote the minimizer by the control pair, control U interval, distributed control and the boundary control. And to these two, this kind of randomized optimal control problem, here is a second question where if the control pair approximates the original one when H is small. And to these two questions, we have the following convergence result. The first theorem tells you that, the solution converges to the original one, and also we can estimate the convergence rate. And I would like to tell you that this convergence rate is just less good than CH, because you can choose the parameter 1 minus epsilon very close to 1. And of course, you will pay this constant very large. So then in this sense, it's not a very bad result. It's almost the result you could obtain for the ODE case. And correspondingly, following the work done by Enrique and Feldman before, you will arrive in the convergence in the controls. And so far, we did not get the convergence rate in the optimal way. And now we can get about a square root of the H of the convergence rate. So we are still improving, try to improving this result. Okay, in the main idea for the proof part, I mainly want to say that an important idea I used for this numerical result is from analysis PDEs. We call it characteristics ODEs. And of course, for initial boundary valued problems, the characteristic curves for PDEs or for wave equations or for these hyperbolic ODEs can be traced back to the boundary nodes or to the initial data. So by PDE analysis, you will know that the solution at any given point t and x in the domain can be presented by the integral along the characteristics. And of course, it may be related to the boundary data or the initial data. And then we can prove that this result tells you that the characteristic curves are not very far from each other when h is efficiently small. And the second result you need is that the point that the curves of the characteristics reaching the boundary are also very close. Then by some cubesum calculations, you arrived to the convergence of the randomized scheme. Okay, at the end of my talk, I would like to show some numerical demonstration for a coupled wave equations in the linear case. And on such kind of a diamond directed graph. So because this is a very common graph in the gas networks or some real world applications, here I just give a very small and easy example. So this diamond graph contains 7 edges and 6 nodes. And of course, there are circles inside. So that's why the normal numerical schemes for calculate that is quite expensive. And in this example, please let me simply choose the linear case to explain the idea. So now I adjust the Neumann control at the extremes or at the joints. So at the joints, I have the classical Kirchhoff transmission conditions and the continuity. So this matrix D here, so tells you that this node is the starting node of the edge or the end node of the edge. So if it's a starting node, we use -1 and the 1 is for the end of each string, respectively. And of course, you give the initial data for such a problem. And we all know that such coupled wave equations can be rewritten into the first order hyperbolic equations we discussed before by introducing the Riemann variables in variables. And here the W minus and the W plus on each edge describes the waves traveling in the negative direction or the positive direction. And then we can summarize the whole networked system in a matrix form, and which is back to our analysis work before. And of course, now the lambda is equipped with the velocity traveling on each edge, which might be different from edge to edge. And correspondingly, the boundary or transmission conditions can be presented as the into domain variable, Riemann variable, is a function of the leaving domain variable, could be minus or one of the minus or the plus one. And of course, the controls. Okay, so in the numerical algorithm, I try to split the network at a node. So here, you will see that on each time step less than h, I only solve the equations on a subgraph. So here the psi E tells you that this edge is be chosen or not be chosen. And then I try to solve a smaller problem on several edges, but not on the entire networks. And here the pi is the possibility of this edge being chosen according to each step. So which could be randomly or given a uniform possibility. Okay, to make it clear for understanding, we see this example. I split the velocity field per edge, and 3 of 7 edges are active at the same time. For example, I adjust the same possibility P on 4 types of subnetworks. you can promise that, for example, I take this A, B, C, D, 4 types of sub networks can cover the original networks. And each time I just choose compute a solution on one subgraphs. And then you will compute that each edge has a different possibility to be chosen. So for the randomized system, it has different velocity that for the traveling waves. And in the simulation, you'll see that comparison of the randomized solution in the orange and the original one. And you will see that it can reduce the computation time 37%. And it stays quite accurate to the original one. And of course, when the P increase, the solution is more accurate. So here I give more simulation result. So now I adjust the same time step, and the P is the size of the sub edges I'm chosen. So at first, maybe I just calculate 1 edge, and the most case I calculate 6 of that. Then you will see that, of course, the error will be less if you compute a larger networks, but of course it's more expensive. And it seems that a potential topic to follow this work is to discuss what is the optimal case. It seems that for such a network with circles or loops inside, the big advantage happens when we cut the loop out. We just consider the tree type networks. So that would be some interesting topic to discuss in future, I think. And for such a wave equation case, we can also prove the convergence result as I discussed before. So now, so far, we discussed the solution in the classical solution way, so C2 solution, and you can prove the convergence in the expectation. Then by the Markov equation, you can also get a weaker convergence result. Then you can adjust the optimal control problems for such a wave equation case, and then you prove the convergence result for the controls. So that is the routine. And for this case, it's easier to get the proof because now the characteristics are with the constant slope. Then you can calculate that it will touch the, for example, the thick one is the original solution, the characteristic curves, it will touch the boundary at this node. And the randomized one may have different velocity, so it will reach the boundary at the other point. So you have to prove that these two types of characteristics are not very far from each other, and also these two nodes are not very far. And of course, due to it with boundary conditions, there are many reflections in between that makes this more difficult in the estimation. So at the end, I would like to show you the summary and perspectives for such a question. The idea to apply the random batch method to the network hyperbolic PDEs combines 3 things. So first is the operator splitting for PDEs. So in that way we can reduce continued PDEs to a randomized one. The second is the stochastics method for large-scale optimization, which we applied on these characteristic ODEs. And of course, from PDEs to ODEs, you need the knowledge that the characteristic method for especially very good for the one-dimensional hyperbolic type PDEs. And by doing that, we efficiently approximate the solutions to networked linear hyperbolic systems so far and associate optimal control problems. We can get the convergence result in the solution when H goes to 0, and also the convergence in optimal controls. But now, as I said before, the convergence rate is not optimal now. I guess we need more regularity properties to guarantee that. So of course, one interesting direction is to extend that to the nonlinear setting. So I think it's straightforward to do a semi-linear case if you have some assumptions on the source term. And on the course linear case, I'm working on that for many years. So we have a series of work of the semi-global classical solutions. And nearby the equilibrium, we can consider the characteristics for such a nonlinear case. And we think that it's possible to use the random batch method so that this has a potential applications on gas networks or water networks. So for the network case, again, I would like to say that this operator splitting setting is not very far to the non-overlapping domain decomposition, which was addressed by the old Lyons from Paris. So we think that the next step is to consider and compare these two types of computational way on a complex spatial structures. And now I'm in the discussion with Gunther Green on this topic. And of course, to a machine learning perspective, one example is to do we call X-pin. You might know the physical inferred neural networks for various type of PDEs. It can be like a PDE solver. And the X-pin is just an extension version of that. So to use the pin on a network setting so that the interface condition will also join the loss function for training. So that is my talk today. I'm enjoying to showing our recent work, and we will finish these two papers maybe in coming months and submit that. Okay, thank you, Lee.
Okay,
thank you. That's my talk today.
Okay, thank you very much, you, for very nice talk. So now we open the turn for comment questions. So if anyone has some questions, please, the microphones are open, so you can ask directly to you your question, or you can just type your question in the chat and you can read it. Okay, okay, I enjoy so much your talk. So I have a couple of question and curiosity. In your main theorem 1,
yes,
you yes, so
yeah.
yeah, so the same question that someone asked me here in the chat. It's about this logarithm lost. Yes, you obtain that in general, or it is optimal,
yeah.
or
I see the question. So I would say in this question setting, it's general, but for the wave equation later, the linear case I show, there's no log term anymore. And this log term happens only when this is how to say the matrix lambda depends on X. So it will change. So for such a kind of setting, this is a very general result we obtain so far. But if it's a linear case, then I don't take the maximum norm of among the space domain, then there's no log. Then you will get the convergence rate just like CH. So like what you can obtain for the ODE case. So we believe that this is the optimal case we could obtain for this kind of how to say when the coefficient depends on x. Yeah.
Okay, so this logarithm comes from the x dependence of
So when your equation, for example, this lambda depends on x. So let's take a wave equation as example. So this is a wave equation. If this velocity c depends on x, then you will get a result also like the convergence rate I obtained here. Because somehow in the it's very complicated in the estimation. Somewhere I have to take the L infinity norm among all how to say the spatial domain, and this term I cannot really kill.
Okay.
But we think we also try to understand that. That's why I write a remark here. So this is not very far from the CH. So I don't know, it's because we are considering PDE and also how to say the non-constant parameter. And maybe that's from there, because any paper Enrique discussed before is just a linear and a constant parameter. They never really consider such a kind of case.
Yeah. So yes, if you think in the nonlinear case, for first order hyperbolic equation.
Yeah.
So this maybe is what we gonna expect to obtain also, no?
Yeah. Nonlinear case, definitely it will depend on x, and if maybe depends on the solution itself.
Yeah.
So we can only do like we can only guarantee a small solution in the neighborhood, for example, 0, or in the neighborhood of equilibrium, and then I try to write the nonlinear version of characteristic ODEs, and then do that. I guess this term will still be here.
Okay. Okay.
Yeah. Thank you.
And also the other question, just maybe I lose some explanation. Is in the when you present the numerical experiments,
Yes.
so you have the reduction -6.
This yes. Yeah, how to say? So how to say? Yeah, so that means that it increased the time even, because I cut the 7 edges into how to say, I calculate in six sub-measures. So it add more steps in the simulation. So in that way, it will not give you a good reduction of time. So it makes the problems more complicated. That's not good. So far, you would say that, for example, I consider a tree type network is very good, or even 4.
Yeah.
Of course, the three edges out of a 7, it's also possible to have a circle, but in many cases it does not. So that's why it seems that it reduced a lot.
Yeah. Okay, good. Yes, so I have no more question. I don't know if is there any other question or comment? Okay, not. So thank you very much for your very nice talk, you. And so I give the word to Anna to